In this video, we're going to be going through reactions of monosaccharides. So let's just review the chemical properties of monosaccharides. So as it seems apparent here, we can see that um, that carbohydrates or monosaccharides are soluble in water due to the presence of many hydroxyl groups, right? And we can see that they're also insoluble in organic or typically non-polar solvents. So with these two key details in mind, let's go through several reactions of monosaccharides, starting with ester formation from monosaccharides, or the polyacylation of monosaccharides. So the reaction conditions for this show that a carbohydrate will react will in the presence of excess ACO2 or acetyl O2 in the presence of a pyridine base will cause the polyacylation of monosaccharides. Okay, so essentially what we're actually drawing here, if we take this molecule and I were to expand on this, we would see the formation of multiple esters. So let's just clarify here what we're showing. Okay. With the formation of multiple ester groups, we can see that what forms is essentially this. Okay, so the reaction conditions is that there must be an excess acid chloride or anhydride used in the presence of a base, which in this case is pyridine. So the reaction is the exact same as the one where alcohols are converted to esters by acid chlorides. So this is just another note on another set of notes that I have for alcohols reacting with acid chlorides. The mechanism here isn't clear to me, at least. I'm not sure if it's well known yet, so I don't really have a mechanism for this reaction. But essentially, these are just the basic reaction conditions required to form a polyacylated monosaccharide. Okay, ether formation from monosaccharides um, is where the formation of multiple is where a carbohydrate reacts in the presence of methyl of a methyl halide, in this case being iodine, in the presence of Ag2O to form a methylated a polymethylated carbohydrate. Okay. Now, I'm not going to draw out the mechanism for all of these for all the methylated steps of forming a carbohydrate, but I can show you one one example. So what happens here is that there's a proton transfer from an oxide ion that has a charge of -2. So it's heavily nucleophilic, or sorry, it readily acts as a base and deprotonates the hydroxyl group. So we see here that there's the formation of an oxide ion, which nucleophilically attacks by SN2 mechanism to get you a methyl group plus plus a charged iodine plus OH, or plus a hydroxyl group that has a charge, and Ag2, silver 2 plus. So we can see that excess. So we can see here in general that in excess, that the general condition is that there's an excess alkyl halide used in the presence of a mild base, such as Ag2O. We're trying not to use strong bases. Moving forward, we have glycoside formation, which is another reaction of monosaccharides where the formed product is a glycoside, where a glycoside is essentially just a monosaccharide with an alkoxy group attached to the anomeric carbon, or in most cases C1, while the other hydroxyl groups remain unaffected. So in essence, we see the formation of a complete acetal. So we can see here that in the presence of 1 mole of alcohol and the presence of an acid catalyst, we can see here that the carbohydrate molecule reacts with the 1 mole of alcohol to form a glycoside, which is just, as I said before, where an alkoxy group is attached to the anomeric carbon only, and this keeps the other hydroxyl groups unaffected. So let's go through the mechanism. The mechanism starts with the protonation of the hydroxyl group of the anomeric carbon. We can see that there is the loss of a leaving group here, where the hydronium ion is pushed out. We can see that there's the formation of a resonance stabilized carbocation. So this carbohydrate contains a carbocation that is stabilized by resonance. And we can see here that a nucleophilic attack occurs by the alcohol. The nucleophilic attack occurs by the alcohol, and we can see by the alcohol, which in this case is just a variable alcohol, or ROH. Right. Now, it's important to note that the nucleophilic attack can cause the formation of 2 stereoisomers, and that depends on where the nucleophilic attack occurs. This is because the carbocation is generally exhibits or is generally shaped as a trigonal plane. Carbon cations are trigonal planar, and therefore we can see that a nucleophilic attack can occur from either the top or the bottom. So in the case of this nucleophile, we can see that on a 3D plane, that in the case of this carbocation, so right here at C1, we can see that the nucleophile can either attack from the top or from the bottom. Okay. And what we see here is the formation of an oxonium ion. And lastly, we have the deprotonation of the oxonium ion to get the formation of 2 stereoisomers, which in this case is beta D-glucopyranoside and alpha D-glucopyranoside, where beta indicates that the substituents of carbon 1 and carbon 5 are on the same side of the ring, and then alpha D-glucopyranoside indicates that the substituents of carbon 1 and carbon 5 are on opposite sides. Okay? It's important to note that the reaction conditions required to facilitate this reaction. So the conditions are that this reaction must be acid catalyzed. The nucleophilic attack occurs from a variable alcohol, ROH, and upon isolation, the glycosides formed can be stabilized under neutral or basic conditions. Okay. Now, N-glycosides are just monosaccharides with an amino group instead of a hydroxyl group attached to the anomeric carbon. So we see here that instead of an alkoxy group, forming, we can see that an amino group forms instead. And this mechanism is just purely speculation, but from what I understand, I think that I would like to think that the mechanism is likely analogous to typical glycoside formation. So we see here. Okay, so we see here that there's the proton transfer, but the mechanism begins the same for both glycoside and N-Glycoside formation. We can see that there's a protonation of the hydroxyl group, and the hydroxyl group, or the newly formed hydronium ion, becomes a leaving group, a good leaving group, right? And then we see that the resonance stabilized carbocation forms, and for this nucleophilic attack, we see that there's a nucleophilic attack of an amine instead of an alcohol. And what we see here is the formation of an N-glycoside that's currently protonated by So we see here that there's the deprotonation of the nitrogen atom of the amine that's attached to the glycoside. And we see here that two products form, beta D and glucopyranoside, N indicating the fact that this is an N-glycoside, that where the glycoside is an amino group instead of a hydroxyl group, or instead of an alkoxy group. And alpha D and glucopyranoside. Okay. Now there are important implications to this, where N-glycosides are essentially responsible for nucleoside formation, can be related to nucleoside formation. And nucleoside formation is where nucleosides are special N-glycosides, in which the monosaccharide is D-ribose. So the monosaccharide that comprises a nucleoside is essentially a 5-member ring. So that's from a particular aldose called aldopentose, or D-ribose. Okay. So D-ribose, so D indicating that the configuration of the chiral center furthest from the carbonyl group is R. Ribose, just the variable name, and aldo indicating that there's an aldehyde. So we can see that the reaction conditions are similar for every other cyclic hemiacetal that forms under the presence of an acid catalyst. And we can take a look here at the mechanism, which is essentially, the mechanism is similar. So when we're looking at the formation of the cyclization of D-ribose, we can see that the mechanism is similar, where there's a proton transfer, there's the protonation of the aldehyde group. The aldehyde is nucleophilically attacked by the hydroxyl group on carbon 4 of aldopentose, which causes the formation of the oxonium ion, which allows for a proton transfer. And then we see the formation of a cyclic hemiacetal. Now, we see here that only the B anomer is formed. And this is because it seems that the carbon bond, the C1-C2 bond does not, for aldopentoses or D-ribose, does not exhibit mutarotation. Okay. Now there's the formation of N-glycosides. Okay. So N-glycosides involving D-ribose or cyclized D-ribose have a similar mechanism. So when nucleosides form, they have a similar mechanism. so under acidic conditions and in the presence of a secondary amine, as it seems here from what we see here, a secondary amine, we can observe the formation of a nucleoside. So let's go through the mechanism. So the mechanism starts with the protonation of the hydroxyl group. The hydroxyl group becomes the protonated hydroxyl group, or the hydronium ion that forms, becomes a good leaving group. And we see this the formation of a resonance stabilized carbocation. And the there becomes a nucleophilic attack, which attacks the carbocation. And we see the formation of a variable amine ion that's attached to the D-ribose, the cyclized form of D-ribose. And then we see that the protonated amine group is deprotonated by the water molecule, which allows for the resulting formation of the N-Glycoside or nucleoside. So there's a couple notes about this reaction here. So this reaction shown here is biologically or biochemically important, as nucleosides serve as building blocks for RNA or DNA, right? The nucleophile is a secondary amine that actually represents nitrogenous heterocycles or bases, and there are 5. There are 5 forms of nucleophiles, or 5 forms of nitrogenous heterocycles or nitrogenous bases that can serve as a nucleophile that nucleophilically attacks cyclized ribose. And these include familiar names such as cytosine, thymine, uracil, adenine, and guanine. Now, if we take a look at their DNA as DNA precursors, we can see here that there's deoxycytidine, deoxythymidine, deoxyadenosine, and deoxyanosine. So these are all DNA precursors, or deoxyribonucleosides, because we see here that there is a hydroxyl group present at carbon 2, and that's why we call them DNA precursors. So if we try to compare, we can see that deoxycytidine essentially contains the cytosine nitrogenous base. Deoxythymidine contains the thymine base. Deoxyadenosine contains the adenine base, and deoxyguanosine contains the guanine base. Now, for ribonucleosides or RNA precursors, we see here that there's cytidine, uridine, which is only present for ribose molecules, and we can see that for all of the ribose molecules shown here, that there is no presence of a hydroxyl group, so we just refer to these as ribose. There's adenosine, which contains the adenine group, or the adenine nitrogenous base, and guanine, which contains guanosine, which contains guanine. Okay? So, just to summarize it all, from a perspective, we can see here that nitrogenous bases serve as nucleophiles in as the primary as the nucleophiles in N-Glycoside formation, and these are the possible ribonucleosides or N-glycosides that can form. Okay. The next type of reaction that monosaccharides can undergo is epimerization of monosaccharides. So let's just go through this reaction. So we can see here that the reverse reaction is actually the forward reaction in the cyclization of monosaccharides. But here we're more interested in observing the reaction with the open form of carbohydrates, which in this particular case being D-glucose. So we can see here that that in its open form, in the presence of a strong base, we can see that the monosaccharide or D-glucose reacts with the hydroxide ion from NaOH in the presence of water to tautomerize the carbohydrate into what we call an N-diol, which is just the formation of an alkene shown here between carbon 1 and carbon 2, and the presence of two allylic alcohols, one alcohol here and the other one here. That's what they mean by N-diol, right? Now, we could reverse tautomerize. So once in the presence of a strong base and water, we can see that the reverse reaction occurs. But now we have the formation of two stereoisomers of glucose, or two stereoisomers of the same aldose, where we see the formation of D-glucose and D-mannose. And we can see here that the configurations here are different. It's likely that this carbon here, or it's likely that the configurations for this carbon here, carbon 2, sorry, I made a mistake. These two, the configuration doesn't, the way that light rotates doesn't change, given that the configuration of the chiral center is still the same for D-mannose and D-glucose. However, we can see that these are still stereoisomers nonetheless, because the configuration at carbon 2 is different. Or the configuration of the chiral center for D-glucose and D-mannose are different. Okay. Now, when these two molecules, or when these two products form, we call these products called epimers, which are a particular pair of diastereomers. The products formed at this particular reaction are diastereomers, since one of the chiral centers, C2, has an altered spatial configuration. So if we do a bit of an analysis here, we can see that D-glucose, or carbon 2, has S configuration, has a supposedly S configuration and therefore R configuration, and D-mannose has a supposedly R configuration and therefore S configuration. This was all determined based on the CIP rules. Okay. Now, the reaction conditions is just the usage of water and a strong base amidst the presence of a carbohydrate to yield epimers. Now, this can be good or bad depending on the context of the situation, and I've only got notes down for how it can be possibly bad. So, in the sense that it's a bad reaction, it yields the yield of the desired product can be lowered since two diastereomers are produced, and hence the reason why we should not use strong bases if we wish to produce polyalkoxylated monosaccharides. Okay. Polyalkoxylated monosaccharides just refers to the reaction that I showed earlier with ether formation. So all the way back at the top. I'm just trying to load the screen so I can show you guys. right here. This is the reason why we use a mild base such as Ag2O if we want to form a polyalkoxylated monosaccharide. Okay. The next set of reactions of monosaccharides includes redox reactions. Okay, so with reducing monosaccharides, we see that aldoses are reduced to form aldoses. So we can see here in this reaction, it's similar to we're interested in the open form of glucose. Okay, and we can see here that in its open form, when glucose reacts with sodium borohydride with H2O as the solvent, we see here that there's the formation of an aldotol, which is just D-glucitol. Okay, so we see here that the ketone group now becomes an alcohol. Okay, so the mechanism shown here is that there's a nucleophilic attack by sodium borohydride, where the hydride ion will will nucleophilically attack the carbon atom of the carbonyl group, and then we see here that an oxide ion forms. That oxide will be protonated to form the alcohol. So sodium borohydride in the presence, so just a couple notes about this reaction and just repeating what I said. So sodium borohydride in the presence of water or suitable bases reacts with a variable aldose to yield an aldotol. And this reaction follows Le Chatelier's principle, where the current equilibrium is where the majority of glucose molecules are in their cyclic hemiacetal form. The equilibrium is adjusted when one glucose molecule in the open chain form is reduced. All glucose molecules will eventually be reduced to satisfy the new equilibrium, and therefore we'll get a 100% yield under these reaction conditions. In essence, we convert all the reactants to product. So it becomes a chain reaction. Once one sugar is reduced, all sugars will become reduced. Let's shift our focus towards the other set of redox reactions, which in this case is the oxidation of monosaccharides. Now, compared to the redox reactions or the reducing reactions of monosaccharides, which appears to only include one method, we can see that there are several methods of oxidizing monosaccharides. So let's just go through all of these methods, starting with method 1, which involves the usage of gaseous bromine in an aqueous solution, which in this case is water, buffered to a pH of 6. Okay, so just ignoring this stuff, this is just the reverse. This is just the decyclization of the monosaccharide, which in this particular case, as an example, is D-glucose. So we can see here that glucose in its open form will react with gaseous bromine in an aqueous solution buffered to a pH of 6 to form gluconic acid, or D-gluconic acid, or an aldonic. D-gluconic acid is an aldonic acid, and we can see here that the carbonyl group that was previously an aldehyde becomes a carboxylic acid, which suggests a change in the oxidation state of the carbon of the molecule, because the carbon, I'm not sure if you've watched my previous videos before, but we can see here that with carbon, they share a certain number of electrons. So carbon being black, carbon owns all of the electrons in this covalent bond with hydrogen. But in the presence of if I were to compare the oxidative states of carbon 1 between the open form glucose and D-gluconic acid, we can see here that carbon 1 only owns the electrons shared with the hydrogen atom, but for the aldehyde, for the C double bond O bond, we see that the oxygen atom owns all the electrons shared in the double bond between oxygen and carbon. That's essentially what's happening for this. That's what's happening for this carbonyl group here. On the other hand, the carbon atom here doesn't own any of the electrons, or doesn't own majority of the electrons, because most of these electrons are owned by the two oxygen atoms in the carboxylic acid functional group. Okay. So essentially, what we see here is a change in the oxidative state of carbon 1 when glucose becomes an aldonic acid. Okay. Now, let's move on to the mechanism. So the mechanism, just a disclaimer that the mechanism here is not actually from the textbook. This is from a different source. I'm not sure if this source can be verified or accurate, but I'll leave the source. I'll post the source here on the on this video later if you guys are interested in checking it out. But essentially here, the mechanism starts with a proton transfer, because the pH is buffered to 6, right? So there's an increased concentration of increased concentration of hydrogen atoms. So we can see here that there's a proton transfer, or sorry, I think I made a mistake here. This is not a proton transfer. This is actually a nucleophilic attack, from what it seems like, because the oxygen atom from this water molecule is actually attacking carbon 1, where we get a chiral center intermediate, and then a nucleophilic attack occurs where the oxide ion that forms will nucleophilically attack one of the bromine atoms in gaseous bromine, forming a bromide ion. That bromide ion will then deprotonate the hydronium ion that's covalently attached to carbon 1, hence a proton transfer, leaving us with HBr, and then we get a concerted E2 mechanism. So we see the elimination of the hydrogen proton, which pushes out the bromine atom to form bromide, and what we're left with is an aldonic acid. Okay. So just a couple notes for this particular reaction. We see that this mild oxidizing agent only works for aldoses, not ketoses. This is because the aldehydic hydrogen present on aldoses that participates in the proton transfer in the E2 concerted mechanism under mildly so the reason why this mild oxidizing agent only works for aldoses and not ketoses is because of the presence of the aldehydic hydrogen present on aldoses that participates in proton transfer in the E2 considered mechanism under mildly acidic conditions. So that means that here in this particular step, that the elimination of this the elimination step here is necessary to form the aldonic acid here, because the transfer of electrons from the hydrogen atom forms a double bond with the between the carbon atom and the oxygen atom, or carbon 1 and the oxygen atom, right? And because this bond forms, that allows us to push out the bromine ion. Okay. And these reagents, or mild oxidizing agents, can be used as a diagnostic test for the following. So we can determine from this test whether the compound is a reducing sugar. And from here on out, let's understand that a reducing sugar is just a monosaccharide that acts as a reducing agent for the reagents, and more specifically for carbon 1. Okay. And we're trying to determine whether the reducing sugar is an aldose or a ketose. And that's based on this fact right here. It all depends on the presence of the aldehydic hydrogen. Alright. Now, for methods 2, 3, and 4, the usage of any of these reagents work with either ketoses or aldoses. So these methods are not exclusive to aldoses. These can also apply to ketoses too, under basic conditions. Okay, so essentially ketones are only capable of acting as reducing sugars in the presence of a base. Okay, so we can better elucidate on this, on how ketones can act as reducing sugars in the presence of a base. So in the presence of a base and in the open form, say for example for a given ketose, we see fructose, we'll see that in the presence of a base we see a tautomerization reaction, which causes the formation of an anidyl, right? And you can see that the anidyl is between it's comprised of primarily carbon 2 and carbon 1. Okay? And then we can see that in the second tautomerization, we can see that the carbonyl group shifts over shifts over to carbon 1. So now the new carbonyl group that was previously on carbon 2 here for fructose now forms on carbon 1, and now what we're left with is D-glucose or D-mannose. And D-mannose. Okay? And because I'm not sure if this necessarily constitutes the idea that these two could be epimer pairs, but we can see here that there are two stereoisomers of the same aldose, right? So we see here that now that there's an aldehyde present, we can see that these sugars are now capable of acting as reducing sugars. So essentially the key idea here is that ketoses in the presence of a base can be converted into aldoses. And then when aldoses are formed, they are then capable of acting as reducing sugars. Okay. So the reactions shown here are very similar to epimerization of glucose molecules, but what we see here is more of an internal rearrangement reaction of the carbonyl group shifting before forming epimers. So the exact same base is used, and so in epimerization, the exact same base is used, and the reactant undergoes tautomerization or isomerization reactions twice. and this is particularly for ketoses, okay? Ketoses. If it was just aldoses, we just directly go straight to epimerization, okay? So with this key idea in mind of knowing how to convert ketoses into aldoses, using a base, let's consider some methods of oxidizing compounds. So we can see here, we can use Toland's reagent. Now, Toland's reagent involves the use of silver in the presence of an ammonium hydroxide ion, or an ammonium hydroxide, plus in aqueous solution, or in this case water. So we see here that in this reaction, we see here the first step is the conversion of D-fructose to D-glucose using the method that I just described here earlier. Just essentially this entire process, right? Next, once the ketose has been converted into an aldose, sorry, just one second. Once the ketose has been converted into an aldose, we can use Toland's reagent, being that silver oxide will convert D-glucose into D-gluconic acid. Okay. Or yes, so because there's the presence of two isomers once D-fructose undergoes isomerization to form glucose. Remember that epimerization occurs where D-glucose and D-mannose forms, and because there's these two products, we also have to consider the fact that once they both react with silver, they get the oxidization of carbon 1, which causes the formation of carboxylic acids. So what we're left with is D-gluconic and D-mannuronic acid. Okay. So the third method of oxidizing monosaccharides involves the usage of Fehling's reagent. So Fehling's reagent is just the usage of a copper 2 ion in sodium tartrate in aqueous solution. So the first reaction is essentially just the formation of an oxidizing agent. So we need to form an oxidizing agent, and this is just the reaction equation used to create Fehling's reagent. So once the Fehling reagent is created, we perform the redox reaction. Okay. Just one second. So with this redox reaction, we see that D-fructose converted to D-glucose forms the formation of two epimers, D-glucose and D-mannose. And then when it reacts in the presence of copper, we're left with D-gluconic and D-mannuronic acid. So the same products in the end, just like when oxidizing monosaccharides are also used. When oxidizing monosaccharides can be used with Toland's reagent, we see the same products formed in both methods: D-gluconic acid and D-mannuronic acid. Okay. Now, there's also Benedict's reagent, which involves the use of copper 2, which also involves the usage of copper 2 in sodium citrate, this time in aqueous solution. So it's essentially the same reaction as Fehling's reagent. D-fructose epimerizes to D-glucose plus D-mannose. You react it with copper 2 with the copper 2 ion, or the copper ion that's with a charge of +2, and you get D-gluconic and D-mannuronic acid. Now, actually, I didn't mention this. So prior to reacting with D-glucose and D-mannose, we can see that that I've written here that the copper ion is currently blue, but once it reacts with D-glucose and D-mannose to form D-gluconic and D-mannuronic acid, we can see that the copper ion forms a red color because it becomes copper 2 oxide, right? And what we see here is that a positive result, or that when it forms a red color, this indicates a positive result. The formation of red precipitate indicates that the oxidizing agent has been reduced in the presence of reducing sugars. Okay, and the oxidizing agent in this case is the copper ion with a +2 charge. Okay, so that's just a key thing to indicate here. So the last method is the usage of a stronger oxidizing agent such as HNO3 to yield a dicarboxylic acid from a monosaccharide. So we can see here that in its open form, in glucose in its open form, in the presence of heat, HNO3 and aqueous solution, which in this case is water, we see the formation of D-glucaric acid, which just refers to a dicarboxylic acid and an alderic, and it's considered what we would consider it an alderic acid. Okay. So on both ends of the carbohydrate, we see that two carboxyl groups form. Okay. Now there's some notes about all of these reagents. So they only serve as diagnostic tests to determine the presence of reducing sugars. They cannot determine whether the monosaccharide is an aldose or ketose upon treatment with the base. This is because of the tautomerization reactions occurring when fructose isomerizes to form glucose and its C2 epimer, D-mannose, upon treatment with a base. Okay. So we move on to the last set of reactions of monosaccharides, which includes chain-lengthening and chain-shortening reactions of monosaccharides. So monosaccharides in their open chain form are capable of elongating or shortening via certain reagents. And for these reactions to occur, the monosaccharide must be an aldose. Okay? So let's go through chain elongation or chain lengthening reactions first. So one such method of elongating the carbohydrate chain is a method called the Kiliani-Fisher Synthesis, which elongates the carbon chain by one atom. So we can see here that glucose and aldohexoses in its open ring form, we can see that it goes through several reactions. The first is the formation of a cyanohydrin. The second step is partial dehydrogenation of the cyanohydrin to form an amine, and then eventually we're going to have that amine pushed out by some sort of mechanism. Okay. That's just essentially what these reaction steps say here, but I think the mechanism should clarify what's going on exactly. Okay, but essentially the key end result of this reaction here is the addition of a new carbon atom, which elongates the chain. Now let me just confirm the general name of the chain, which I believe is an aldopentose. I'm not sure if that's correct. Yes, an aldohexose. So an aldohexose is what results after the new carbon atom is added. Okay. So let's go through the mechanism. So The mechanism starts with a nucleophilic attack by a cyanide ion, okay? And let's understand that this nucleophilic attack is non-stereoselective when it attacks the carbonyl group. So we can see that two epimers will form, and these are called these are C2 epimers. So let's keep in mind from here on out that there will be two products, at least two products that form at the end of this synthesis. So once these two epimers form, we get a proton transfer from the hydrogen atom that's attached to the cyanide ion. So upon the proton transfer, we'll see another cyanide ion forming, and what we're left with is what we call a cyanohydrin, where both the cyan group and the hydroxyl group are on the same carbon atom, which in this case is carbon 1. Okay. Now the cyanohydrin, or the cyanide functional group, will particularly be partially hydrogenated in the presence of gaseous hydrogen and I believe platinum and barium sulfur oxide. I can't remember the name of the exact compound that were used to facilitate this reaction, or maybe this must have been lead. Let me just confirm this for a second. PD. Yeah. PD chemistry. No, sorry, this is palladium. Okay, so in the partial hydrogenation step, we see that the cyanohydrin is hydrogenated to form an amine. Okay. Oh, and here the amine will be protonated by a hydronium ion to get a protonated amine, and then this amine will be nucleophilically attacked by a water molecule to get to form an attack. So this water molecule will nucleophilically attack the carbon atom, which will become which will subsequently become a hydronium ion that's attached to the carbon atom that was previously an amine, and then there will be another proton transfer by another water molecule, where the water molecule is protonated by the hydronium ion. And what we see here is the formation of a carbonyl amine, where ol just indicates that there's a hydroxyl group attached to the same carbon that is also attached to an amine. That we see here is attached to an amine. Now let's just label this carbon as carbon 7. So from here on out, this carbon will be labeled as 7. Okay. So the amine group will then be protonated by another hydronium ion in both these epimers, and then this protonated amine will then become a good leaving group since it has a positive charge, and at the same, but it won't just serve as a regular leaving group. What we'll see here is a 1-2 elimination. Okay, and then from this elimination, we see here that an oxonium ion will form where there's 3 bonds attached to the oxygen atom, and it has a positive charge. Okay, this oxonium ion will be deprotonated by water, And what we're left with is a pair of epimers that are now 7 carbons in length, 7 carbons of length in length. So we can see here the formation of a carbonyl group. Okay. And lastly, we have the last reaction type of reaction for monosaccharides, and the other set of changing the length changing reactions. We have chain-shortening reactions, which are just which in this particular case, or this method of chain-shortening reactions, we're dealing with Wohl-Degradation, which shortens the carbon length, or shortens the carbon chain by 1 atom, by 1 carbon. So the glucose in its open form will undergo a series of reaction steps to form diarabinose, and we'll clarify this in the mechanism. Okay, so here's the proposed mechanism. So this mechanism, actually both of these mechanisms have yet to be verified. The previous mechanism for chain lengthening reactions was actually just a prediction based on what I understood and what I had based on previous knowledge. Like, a lot of these reactions are derived from previous concepts that were covered in organic chemistry, so they're not. This mechanism isn't necessarily accurate unless proven otherwise. Okay, so just keep that in mind as we go along with these mechanisms. Now, this mechanism here, this starts with so the end goal here is to reduce the carbon length of the chain by 1 carbon, right? So what starts off as D-glucose will end in diarabinose, or an aldopentose, right? So we see here that for the first step of this mechanism, we'll see a nucleophilic attack. Okay. What we'll see here is by an amine that has as a hydroxyl group as one of its substituents. So we could consider this to be a primary amine, because there's essentially R as one of the substituents, one of the variable substituents. Hydrogen atoms don't count. Okay, so under this case, we see that there's a proton transfer from a hydronium ion. Okay, and this hydronium ion will then undergo, and then the ammonium ion that forms will reprotonate, or will be deprotonated by a water molecule, and then what we're left with is a similar intermediate called intermediate molecule called a carbonyl amine, right? Where both the both the amine and the hydroxyl group are attached to the same carbon, which in this case is 1, right? The carbonyl amine will be protonated, or the hydroxyl group will be protonated by the hydronium ion, which will cause the formation of an oxonium ion. And what we're left with is an arrow pushing mechanism that allows for the leaving of which allows for a leaving group to leave the molecule. So the leaving group in this case will be the oxonium ion, or what becomes water afterwards, right? And we're left with an aminium ion. Okay. Now the aminium ion will be deprotonated by a water molecule, which will leave us with a unique molecule called an oxime. I would assume that an oxime refers to a variable imine where the imine is actually attached to an oxygen atom, hence the name oxime. Now, the oxime will nucleophilically attack a molecule called ACO2. I think the name has actually been spelled wrong. I think it's AC2O. Let me just confirm. AC2. Yeah, acetic anhydride. I labeled this incorrectly. It's just actually like this. AC2O. Okay, so the oxime will nucleophilically attack the acetic anhydride molecule labeled in yellow, and then we'll get the loss of a leaving group. Okay, now let's actually make sure that we understand exactly what's going on here. So we can see that a positive charge forms on the previous oxime, and we can see here that there is a positive charge on this oxygen atom, right? But essentially what we'll see here is a loss of a leaving group, where this will just simply become an acetate molecule, right? Now that acetate molecule will essentially participate in a proton transfer, and that will essentially will allow the next step to occur, where there is a rotation of the nitrogen-oxygen bond to favorably allow for what we call an elimination intramolecular, or EI. Okay, so essentially for this intramolecular elimination, we can see here that this bond will be cleaved. Okay, right, and then this bond will also be cleaved, right? Essentially, we're seeing here a proton transfer and the cleavage of two bonds, right, which allows the leaving group to be an acetic acid. Okay, so acetic acid essentially leaves once this elimination intramolecular reaction occurs, and then what we're left with is a cyanohydrin, right? And once that occurs, we can see here I've kind of expanded from carbon 2, so carbon 2 is a little more expanded now. Make sure that we note here that the cyanohydrin is comprised of both C1 and the nitrogen atom. Okay, so that's important to understand because that cyanohydrin will be a leaving group, right? When this hydrogen atom is, or when a proton transfer occurs, we'll also see the loss of a leaving group, which is essentially the reason why this is called an E2 mechanism, a considered E2 mechanism, right? And what we're left with is D-arabinose. Okay.